Hi, class. Welcome back. We're going to finish up the second half of Chapter 9, Plate Tectonics and Landforms today, a brief overview. So let's do it. So we're moving into volcanic features now. Now these are features, of course, that are created by volcanic eruptions. So they will usually produce landforms made of igneous extrusive rocks. So we're going to look at four particular features here: the strato or composite volcano, a shield volcano, a cinder cone, and caldera. And yes, there are more volcanic features, but these are the four I'd like for you to know. So a composite volcano or stratovolcano has stratified layers of solidified ash and lava inside. So basically, from an eruption, you may get ash and lapilli falling down onto the side of the volcano, followed by an effusive eruption of lava, which then solidifies. And next time, we're going to have another eruption with ash and then some lava. So we build up these layers on these composite or stratovolcanoes. One thing you'll notice that the sides of these volcanoes are pretty steep, and that's a reflection of the high silica content within the magma. So whenever you see a steep-sided volcano with alternating layers of ash and solidified lava, that is indeed a composite or stratovolcano. And again, they tend to get steeper towards the top here. Now think about that. A very viscous magma coming up has to find its way through the cracks here and get out. Well, if pressure builds from below before that magma can get out, that pressure could actually lead to an explosive eruption. So composite volcanoes or stratovolcanoes are typically known to be quite explosive. This is what they look like in reality. So you don't get to see the different layers until you dig down, but steep sides, and especially ones that get steeper towards the top. This is El Misti volcano in or near Arequipa in Peru. And sometimes these volcanoes can erupt violently, so explosive eruptions. And as we'll see later on, this little column of ash and pulverized rock, superheated, moving down slope, these pyroclastic flows, they can be very, very dangerous. Now, the second type of volcano is referred to as a shield volcano, and it looks like a shield lying on the ground. These are usually quite large in size, but the magma here is very low in silica, so it will come out of the vent and just flow and flow and flow before it solidifies. So it doesn't build up very steep slopes. Instead, it builds up pretty shallow slopes. Many times these are made out of a basaltic type rock, so low silica content, higher in magnesium and iron content. So when the magma comes out, flows as lava, it will flow for many miles in some cases, building up these huge volcanic features. But again, the key is the slope is not steep, it's very shallow by comparison. And these are usually associated with what we call effusive eruptions. That means the ones that flow versus those that explode very violently. So once the eruption is over, you get a very low angle volcano. Not as much ash as there is lava. In fact, these are predominantly made of solidified lava. And in this case, Mauna Loa in Hawaii, very, very basalt rich. So again, those flows, typically these are going to flow a few miles per hour, or maybe even just a few feet per hour. Within the channel, we can get a faster flow of lava across the surface. So don't let the size fool you. This is Mount Rainier, a stratovolcano for comparison size here, just the one that's outside of Seattle, Washington, versus that Mauna Loa Kilauea volcano on the Big Island of Hawaii. Huge by comparison. But again, it's the angle of the slope that tells you if these are going to have effusive or non-explosive eruptions versus, in this case, Mount Rainier, a very explosive eruption. Our third type is referred to as a cinder cone. These are made out of ash and cinders or lapilli that basically will be semi-solid, if not solid, when erupted from the volcano. They those pieces will roll back down and glue themselves to the sides of this volcanic feature. Since there's not much in the way of lava inside of here, we can't call it a stratovolcano. These tend to be much smaller in size also. But digging through here, you find mainly solidified ash lapilli, cinders basically. So we call these a cinder cone. This one is at Coso Junction. If you drive from LA towards Mammoth Lake, it marks about the halfway point. There's a rest area up there. And this one is called Red Hill because the cinders that solidified to make this cinder cone had a higher iron-rich content, and they will rust out to that red color. So Red Hill. You look for the sign that says Fossil Falls, Cinder Road. You can find that halfway to Mammoth Lakes. Now, our last volcanic feature we're going to talk about is called a caldera. Basically, a caldera is a collapsed volcano. So you can imagine a stratovolcano with a massive eruption, so the magma from the magma chamber erupting out, that will create a big hole here. It's like shaking this whole mountain up, cracking it up, sort of like imagine a champagne bottle. Get a champagne bottle, shake it up like crazy, heat it up, shake it up, heat it up, shake it up, and then pop the top off. All that champagne that was in the bottle is going to come out. Well, all this superheated magma with lots of gaseous bubbles in there, out it comes, and that will create a big hole after the eruption. And then the top of that volcano that was all cracked up will fall back down into that hole. So basically, what was here has been erupted away violently. The magma is all gone, and basically the volcano has collapsed into that hole. So now the high point is on the outside of this caldera rim. Remember, caldera, a collapsed volcano. That means it's usually a low spot inside, and when we get rainfall, it's going to start filling up. So oftentimes we get these calderas with lakes filling inside. That's if it's higher than sea level. Sometimes we'll see if these are at or below sea level, they'll fill with seawater. This is in Oregon. This is Crater Lake, one of our national parks. This is basically a caldera edge right here. And now we have subsequent magma coming up, forming lava flows that will basically start filling this caldera in. So this is Wizard Island in within the caldera of Crater Lake National Park. So you can see the edge of the caldera marked here. These resurgent domes here, basically Wizard Island, and others that have not yet made their way to the surface. So this over time will start filling in with subsequent eruptions and create a stratovolcano again, which may erupt and form another caldera. It is possible to have multiple episodes. Mammoth Lakes was a caldera that erupted violently about 750,000 years ago. If you ever drive to Mammoth Lakes, you'll be coming up Highway 395 and then shooting off from that Highway 203 into Mammoth Lakes town. But basically this red line here would mark the edge of that caldera from that eruption 760,000 years ago. Subsequent to that, probably about 200,000 years ago to about 50,000 years ago, these resurgent eruptions within that caldera came up to start forming Mammoth Lakes itself. So Mammoth Lakes is, or the mountain, Mammoth Mountain, is the result of eruptions after that caldera formed. Like my animation and artwork here, this is a caldera on the island of Bali, and this is called Mount Batur. So Mount Batur had two violent eruptions 20,000 years ago and 29,000 years ago, forming the present-day caldera. I'll show you that image here. So here's the present-day edge of the caldera. This is the one that formed 29,000 years ago. After that, it would have filled in with some eruptions, as it's doing today. And there was a secondary caldera formed right here within the older caldera. That one's from the 20,000 year ago eruption. And now we have more volcanic events filling up the younger caldera with the current Mount Batur that sits about 5,700 feet above sea level or so. So you can climb that in the early morning hours if you get to Bali ever. And from the top of that at sunrise, you can see volcanoes across a whole chain from Bali to Lombok and beyond. One of the world's most famous calderas is that of the island of Santorini or Thera in Greece, in the Cyclades Islands. And this is a caldera rim. It's a beautiful place to go. If you do ever get a chance to go check out Santorini. It's one of the most phenomenal places on the world. It's visually stunning. This is from the town of Ia, looking over towards Thera town over here. The ships come in over this way, let you up. So if we look at this map of active volcanoes around the world, at any time we have about 1,500 active volcanoes. That doesn't mean erupting, but active. We'll find out in a minute. Active means that there's been some kind of volcanic activity within the last 10,000 years. So in geologic time, that's like yesterday. So if something's erupted within the last 10,000 years, good chance it's going to do it again. But more interested in this slide is the distribution. You can see where most of the world's volcanoes are. And we've touched on this a little bit, and we can explain an awful lot about why we have volcanoes where we do, such as along the west coast of South America, because of oceanic continental collision. We have them across the eastern portion of Eurasia, largely because of oceanic continental or oceanic convergence. In the middle of the Pacific, because of the hotspot of Hawaii. So we can identify an awful lot of why these are going on and where they are in terms of volcanic activity. So as I mentioned, we have to describe these volcanoes based on a few criteria. You've heard the word before, extinct. An extinct volcano means that the process that created that volcano in the first place is probably no longer in existence. So maybe there was subduction going on in the past, creating volcanoes in a certain area, and that subduction is no longer occurring. So that would be an extinct volcano. A dormant volcano is a volcano that has not erupted within the last 10,000 years, but it's expected to do so. So some volcanoes don't pop their tops except for maybe every 100,000 years or so. So again, 10,000 years is a bit of a blip. So if we think the processes that created a volcano that last erupted 100,000 years ago, those processes are still at work, we would call that volcano a dormant volcano because we expect, well, that may indeed erupt again. Now, an active volcano has erupted within the last 10,000 years. So there's evidence of it erupting in the last 10,000 years. We would still call that active. Now, to be active, it doesn't mean it has to be erupting right now. That's called an erupting volcano. So an erupting volcano is a form of an active volcano. So active volcanoes erupted within the last 10,000 years. They're either erupting right now or they're not erupting. But if they're not erupting, they can very much still be active. Now, sometimes the magma coming up towards the surface doesn't make it to the surface. It doesn't create a volcano. That magma doesn't have the energy or the heat to make it all the way through, so that magma will solidify within the crust. And in that case, it's going to form igneous intrusive rocks. Let's take a look at some of the features that might be created from that. First of all, blobs and blobs and blobs of magma coming up over time, maybe millions of years, maybe tens of millions of years, maybe over 100 million years of blobs or plumes of magma coming up and solidifying within the crust. That happens quite often. So basically, we get this big, massive blob of igneous intrusive rock that's formed. Remember that number one igneous intrusive rock is granite, so we'll say a lot of granitic type rocks forming this massive amount of rock within the crust, this igneous intrusive rock. Now later on, that might get uplifted, all the rocks above eroded away, exposing this big, massive igneous intrusive rock, we would call that massive amount a batholith. So a batholith is an absolutely huge amount of igneous intrusive rock uplifted and exposed at the surface. To be honest, while it's still underground, it's still referred to as a batholith, but because this is geography, we look at the stuff at the surface, so we will call those at the surface a batholith. A smaller version of that is referred to as a stock. So a stock is a small batholith, and a batholith is a big stock. Now, very often we get some of the magma finding a crack or cracks or burning a hole through the crust and basically then solidifying below the ground. Now, the stuff that made it to the surface would certainly then flow and give us igneous extrusive rocks. But imagine the stuff still below the surface that solidifies very slowly and has cut a vertical path through the pre-existing rocks, and that vertical path would then solidify as igneous intrusive rock if it remains below the surface. Now, if it's cutting a vertical path and then solidifying, we refer to that as a dike. Sometimes that same igneous intrusive, sometimes that same magma makes its way towards the surface, but then will squeeze between pre-existing rock layers and then solidify. So this would be a horizontal layer of igneous intrusive rock once it's crystallized or solidified. So if we see layers of sedimentary rock and then a layer of igneous intrusive rock and then another layer of sedimentary rock, we know that that igneous intrusive rock must have squeezed between some sedimentary rock layers while still underground. Don't worry about laccolith. That is basically an emplacement of magma that lifts up the beds above it before solidifying. So it's very much like a sill. A sill doesn't lift up the beds above it, where a laccolith does. For a geology class, that's important. For a geography class, less so. I want you to identify some basic features. This shows you the igneous intrusive rock that formed when it cut through, or when the magma that formed it cut through sedimentary rock layers in an almost vertical pattern, giving us a dike. So basically, this is that same diagram here. This is what it would look like once all the rocks above have been eroded away, exposing that very hard granite. And this is what it looks like in reality. So sedimentary rock layers over here, horizontally laid down, and then dike formed by cutting through. So that's what you see right there. Sedimentary rocks and this igneous intrusive rock. It must have cut through those rocks. So that's a dike. A batholith, as we said before, give 100 million years or so for magma plumes to come up, form in the crust, solidify in the crust, and then get uplifted. So there's an earthquake fault along the base of these mountains, and that's been uplifting all these rocks. Everything that was above eroded away. Some of that went to the west, some of it came to the east where we're standing, and basically filled up this valley. So these are all the sediments of the rocks that used to be up here. And this is predominantly granitic rock making up the Sierra Nevada batholith. So this blue line here shows the extent of that. Hundreds of miles by many tens of miles wide. Now, we're going to look at what happens when you've got layers of the crust that are compressed together, or when they are, well, let's start with that first of all. They are compressed. It's called crustal shortening. They are basically pressed, and those layers will bend up and down and up and down if given the chance, creating what we call folds or bends in bedrock. So let's take a look at those. Anticline, syncline. Those are the two I really want you to know. Again, sedimentary rock layers, they're compressed, and so those rock layers bend up and down and up and down and up and down, so forth. So really what you to know is what we call that downward bend in bedrock and what we call the upward bend in bedrock. Those are the two most important ones. Okay. Sometimes we'll see that the beds get overturned a little bit, and sometimes they break. Well, if they break, that's no longer a fold. That would be a fault. So not a fold, but a fault. But these are folds with a D, folds in bedrock. So a downward fold in bedrock we refer to as a syncline. and an upward fold we refer to as an anticline. So anticlines tend to create the backbones of mountains, and synclines tend to create the valleys between them. Now, what's important here is if you were looking for oil, you want to locate where anticlines are located, because if there's any oil-bearing rocks below here, they tend to squeeze the oil into these pockets, and you can drill down straight into those pockets to see if there's any oil there. So I want you to know anticline, this one here, and I want you to know syncline. Syncline is a downward bend, and anticline is an upward bend in rocks. So what is this? You have to think back a little bit. These are sedimentary rock layers right here. Looks like mostly limestone. And this is igneous intrusive rock cutting through vertically. What is that? I know what you're thinking. Yep, that's a dike. That's a dike. Igneous intrusive rock cutting through layers of sedimentary rocks. So the sedimentary rocks would have been there before, and then a plume of magma came through and solidified in between those rock layers. What about this? Here's an upward bend in bedrock. That's referred to as, yep, that's an anticline. Now remember, sometimes we got rock layers that go up, and look over here. They're bending downwards. That would not be an anticline, would it? That would be something else. You know what it is. Just like this one. Downward bend in rocks, beds of rock. That is a syncline. So be able to identify those if you see them in nature. Now faults are when the earth crust breaks. So when we get the breaks in the bedrock, we call them faults with a T instead of folds. So we can divide these into 3 or 4 different types. If we go to 3 types, we would say normal, reverse, and strike slip faults. Normal faults are when the rocks are pulled apart, reverse or thrust faults when they're thrust together, and strike slip when they move side by side. So again, normal faults when the blocks are pulled apart, strike slip when they move side by side, and reverse or thrust faults are when they are thrust together. Now these two are pretty much the same thing. Some people like to say, well, if it has a very low angle to the fault, we call it a thrust fault. And when we have a high angle to the fault, we'll call that a reverse fault. But they're pretty much the same thing, like in this diagram here. Reverse faults or thrust faults when they are pushed together. Here's the fault line right here. Normal faults when these two blocks are pulled apart. That happens a lot in the eastern portion of California. They're called normal faults because it was the first type of fault that was named. The reverse fault is the opposite of that, hence that's how it got its name. And strike slip faults are when the blocks of land are pushed not up or down relative to each other, but side by side, like with the San Andreas fault. Movement along a fault line in California near Hollister. Here's the fault line running this way. This portion of the land is moving to the right, this portion to our left. We would name this strike slip fault based on which way the other side moves during an earthquake. So the other side of the fault moves to the right, so we call this a right lateral strike slip fault. And by the way, if you were standing over here looking back this way, this side would have moved to the right of anybody standing over here looking our way. So still a right lateral strike slip fault. And what's going on here is we do have a fault line running right through here. And basically, this side is moving to the right, and this side is moving to our right. If we were standing over here, this is also a right lateral strike slip fault. And what we see here is some offset stream channels. This stream connects over here. So this used to be lined up over here, and after subsequent earthquakes, the stream bed has been moving over in this direction here. As it's done so, the stream has actually moved along the fault and then found its stream bed again. So these are called offset stream channels, very indicative of strike slip faults. Okay, Geologic hazards. I want you to know a few geologic hazards before we're done. We don't have any volcanoes anywhere near Los Angeles, so we don't have to worry so much, but many of you are travelers, so you're going to go to other parts of the state and country or the world where there are vol volcanoes, and I want you to take a look at some of the things associated with them. So we're going to look at some geologic hazards associated with volcanoes, some associated with earthquakes, and especially things like tsunami. Now, liquefaction and landslides and things of that nature, I'm going to leave for another time. So basically, if you're anywhere near a volcano, you've certainly got to watch for an eruption itself with that pyroclastic flow, that superheated gas and mushed up rocks flowing down the mountain at very fast speeds, maybe 100 kilometers or 100 miles an hour in some cases, 2,000 degrees. That would burn the heck out of you. So you got to stay away from those pyroclastic flows. Sometimes the ash mixes with water and flows down the hill, what we call a lahar. Oops, sorry, right here. My cursor's not doing very well. Come on, here we go. Mixing with the water with a lahar. Lava flows themselves do not travel quite as fast as the movies tend to show you. So basically, it's not the lava flow you have to worry so much about as it is the pyroclastic flows, or later on with the mixing of water and ash into these lahars. There are many, many, many things. I mean, basically, if you're near an eruption and you're getting hit by lava bombs, you're too close to that eruption anyway. Watch out for the ash, because much volcanic ash is toxic. It's also like really sharp needles. You breathe them in, and it's very bad for your lungs. And also, the ash can build up onto structures, and actually, with the weight of that, collapse those structures over time, especially in developing countries. So here we're showing a pyroclastic flow, Mount Merapi in Indonesia. Basically, anybody in the path of this would be toasted. So you've got to be very careful of these pyroclastic flows, superheated gas clouds coming down the mountain at very fast speeds. So when the volcano is in an eruptive mode, the authorities usually make people stay away from a zone, and it's that zone is to prevent them from being toasted by one of these pyroclastic flows. A lahar that came down from Mount Mayon in the Philippines. So there are people trying to cross right here. Probably not a great idea. This is like a mix of volcanic ash and water, so it's very viscous. It's very, very heavy. So it wouldn't take very much of this to wipe you off your feet and send you downstream. One of the eruptions that people often talk about in North America is that of Mount St. Helens in May of 1980. Mount St. Helens blew its top, ash landing all the way on the other side of the Rocky Mountains. And that's a pretty big eruption in U.S. history. But if we look in terms of global activities here, if I can just get this cursor to move, come on. Here we go. Mount St. Helens was a tiny, tiny, tiny eruption. So tiny it's covered over by my head over here. It was the tiniest eruption by comparison to others we've had. Yellowstone. So imagine a dot. It's too bad my head is covered in this stuff. A tiny, tiny dot over here, Mount St. Helens. Yellowstone eruptions will be massive by comparison, but luckily we don't get them except for every 3/4 of a million years or so. So Yellowstone, the Long Valley caldera that formed the caldera in Mammoth Lakes. These are massive eruptions by comparison. So we haven't had very many large eruptions. Krakatoa over here, but Mount St. Helens would be about a tenth of that. Tiny eruption. So when we're looking at large eruptions in our own memory, they're not large in terms of those that we've had in geologic time. Okay, I had to move locations there because the dogs were barking like crazy in the background. So earthquakes, we're going to not only look at the fact that earthquakes will shake the ground, but how do we measure that ground shaking? So there are two scales I want you to be aware of. One is called the Mercalli intensity scale, and the other one is a moment magnitude scale. So let's take a look at those. First of all, why do we even have these? So basically, when we have an earthquake, the stresses that have been built up will be released. The ground will shake, not only on the surface, but remember we also have those S waves and P waves traveling through the crust of the Earth too. But at the surface, we're going to feel that. And we can feel that so strongly that buildings will collapse, like here in Nepal in April 2015, but also in places like Northridge. So back in 1994, we had a 6.7 magnitude earthquake, and that created quite a bit of damage to places like this Kaiser Permanente building. That was an office structure. The brand new parking lot at Cal State Northridge. Gas lines bust, and we had major fires from that. And the Northridge Fashion Center, the shopping area, we saw a lot of collapse of buildings there. So we're not immune to this. So how do we measure the kind of damage? Well, first of all, the damage itself is measured on something called the Modified Mercalli Intensity Scale, or MMI. This is not the one you're most familiar with, but this is one that geologists would use to look at how much damage has been done. And of course, in this case, if you're closer to the epicenter of the earthquake, you're going to see quite a bit of damage. As you move further away, you're going to get less damage, and it all depends on what the intensity of the earthquake was. So if we look at Northridge really quickly, the epicenter of the earthquake was in this area right here, and we see quite a bit of extensive damage in the orange areas, but most intense damage in these purple areas here, which we found out later on through analysis was related to waves of energy bouncing off the bedrock of the valley and basically coming back up in certain areas and creating extensive damage, not only very close to the epicenter over by Northridge. Well, actually, the epicenter was really in Reseda, California, but we called it a Northridge earthquake because of the initial damage reports. And up towards Santa Clarita, areas of a lot of damage, and West LA, a lot of damage too. So we use the MMI scale to show just exactly how much damage was done. Now, for the most part, though, we measure earthquakes by how much energy is being released. We used to do this using the Richter scale, but we found that doesn't work for large earthquakes. So in the 70s, we developed something called the moment magnitude scale, or MMS, as a replacement for the Richter scale. Now, this will not change depending on how far you move away from an earthquake, because it's telling you how much energy is released. So a magnitude 6.7 earthquake at Northridge is a magnitude 6.7 earthquake. It's not going to change as you move further away. Yes, the damage will change, but the magnitude of the earthquake will not. And of course, the closer you are to the epicenter, again, you're going to feel it more. So this is a number one way of measuring earthquakes. We don't use the Richter scale anymore. Only the people in the newspapers do that, or on the TV broadcasts. Everybody else uses the moment magnitude scale. And that's a scale that, again, tells you just how much energy is released from an earthquake, and it's measured based on the strength of the rock material, how much the fault moved or how far the fault moved, and also the area of movement, not just the length, but the area of movement. So once the scale is put into a mathematical equation, it comes out with a number that is logarithmic, and what it tells you is that every step from a magnitude 2 to a magnitude 3, the magnitude 3 would have 32 times more energy being released than one order of magnitude lower, sorry, one order on the scale lower. So magnitude 3 has 32 times more energy having been released than a magnitude 2. A magnitude 4 would have 32 times more energy released than a magnitude 3, and so forth. So there's a video I posted. I want you to look at that and how we measure and how we look at that scale. So large earthquakes themselves. These are the largest earthquakes since the year 1900 across the planet. And basically we're looking at anywhere from magnitude 9.5 down to the mid 8s. And look at the locations here: Chile, Alaska, Sumatra, Japan, Kamchatka in Russia, Chile, Ecuador, etc. All the way down to Sumatra, Alaska again. It looks like they're all over the place in terms of location until we place these on a map and see exactly where they are. And of course, this is the Pacific Ocean, so they're all on or around the edges of the Pacific, or where we have, in this case over here, where we have continental collisions taking place. Do you notice that some place is missing? Not many earthquakes over on this portion. And that could be, so that basically the northeast portion of the Pacific Ocean, it could be because of the strength of the rocks that we get smaller earthquakes, or it could be that we're overdue for large earthquakes. Nobody really knows, but we're working on that. So largest U.S. earthquakes? Any state come to mind? Any state keep popping up in mind here? So 10 of the 12 largest earthquakes in the U.S. ever recorded are in Alaska. This one here, the Cascadia subduction zone, is off the coast of Washington State and Hawaii. So basically, we don't see California on this list very much, do we? Yet most people think of earthquakes, they think of California as a place to worry about. It's Alaska you got to worry about. So if we look at the lower 48 states, even so, we got that earthquake off the coast of Washington State, and then lots in California, and then, whoa, what is this? Missouri. Yep, back in 1812, we had major earthquakes in what was the old, we find out the Missouri and Mississippi systems are probably built on very old fault zones that still have some energy they release every now and then. And finally, we got more California earthquakes, like the 1872 earthquake in Owens Valley. Again, that's on the way up to Mammoth Lakes. There's a monument there to the earthquake. But the big one here for California thought would be 1906 in San Francisco, which was then a very growing city. So if we had that same kind of earthquake now at 7.8 magnitude, we'd be experiencing considerable loss. So California earthquakes, if we look at these, we're looking at back in 1906, 3,000 or more killed in San Francisco. We don't see that many people being killed in recent earthquakes. One, because they haven't had very large earthquakes by comparison to other places. So most of these have been in the sixes, but also because we do build for earthquakes these days. So a lot of structural damage, but not a lot of people killed. And by the way, in most of these recent earthquakes, about half of the people killed were from heart attack. So one of the things you can do is prepare for an earthquake and relax during the earthquake, because there's very little else you can do during that earthquake. Now, one of the things that another hazard associated with earthquakes are those of the tsunami or seismic sea wave. And that occurs when we get the bed of the ocean being disrupted on a wave of energy, not a physical wave of water, but a wave of energy that will develop into a wave of water later on, like in December 26, 2004, magnitude 9 earthquake off the coast of Sumatra, sorry, off the coast of yes, the island of Sumatra in Indonesia. And that would send a wave of energy throughout the Indian Ocean, especially the coastal places nearby. Like Malaysia, these are waves of energy forming into physical waves approaching the coastline of Malaysia. You can see in the background here, very large waves developing here would end up being probably 20 and 30-foot high waves traveling considerable speed. Now, across the open ocean, the energy is traveling about the same speed as a plane, 500 miles an hour or so. But as that energy wave starts to hit a coastline, it slows down at the bottom and the top keeps going. So basically it builds up a wave, slowing down. But even so, when it hits the coastline, we get this water traveling at maybe 30 or 40 miles an hour, maybe more. But that big wave has built up. So we got here large waves, 20 to 30 feet, about to crash down onto the coastline here with these people running away from it. They better get to high ground very quickly. Because if that wave hits and it churns everything together, so it's like a big mixing bowl traveling along with pieces of concrete and reef and poles and all kind of stuff in it, it scours everything away. So basically, this is the city of Banda Aceh in the northern tip of Sumatra before, and this is what like afterwards. Not only is there standing water, but most of the buildings have been churned away, most of the vegetation gone. So there's very little way of surviving a large tsunami. It's just something you want to avoid rather than try to make your way through. Again, Banda Aceh, oblique aerial photograph here. Not very many places to hide right there. Same thing happened in Japan in March of 2011. Large tsunami following an earthquake, an offshore earthquake, and basically we have waves in some of the areas here that are 8.5 meters. That's about 30 feet of wave right there hitting these coastlines, including up by Fukushima, where the nuclear reactor was destroyed, basically. So if there's an earthquake, if you feel an earthquake, if you're at the beach, get to high ground right away. The difficulty is these waves travel across entire oceans, so the earthquake could be thousands of miles away. But luckily, we do have an early warning system, so sirens will go off in most coastal places these days, warning people if there's even a faraway earthquake that could have generated a tsunami coming your way. But if you ever are at the beach and the water starts to recede inexplicably, the water starts to recede away, that could mean that a wave is building offshore and coming your way. So get to high ground as soon as you can. All right, that's the end of chapter 9. That's the end of the course. And I think we're done for now. I believe that you're going to have tons of questions. So let me address those in our next office hour. And we'll try to do that as a Zoom session. Okay? Take care, everybody.